Introduction to Flip. So this is hopefully going to be not too long. I'm going to try to go over the basics of flip simulation, basically where it came from, what other types of fluid simulations there are, different methods, and try to break that down so you have a bit of a better understanding, if you don't have already, of how flip simulations are created, and therefore might be easier to tackle problems, issues that you encounter if you're doing simulations in Houdini. First off, let's start with a fairly standard approach, which would be the Lagrangian method. This is just calculating fluid simulations with pure particles. I mean, that's not the Lagrangian method, but calculating fluid simulations with pure particles is called the Lagrangian method. It's probably the most accurate method for physical processes. It's basically point cloud moving through space, and attributes such as mass, velocity, and viscosity, they're stored on a per point basis. So if you would imagine yourself on a river and you're sitting in a boat and just traveling along with that river, so basically with the flow, that way moving with the particles. There are some drawbacks with this method. The main one is incompressibility, meaning mass conservation is hard to track because you have to calculate on a particle interaction on a per point basis. So basically calculate interaction forces with millions of particles. And this can get pretty slow. I think the main simulation method for this is SPH that you probably know, smooth particle hydrodynamics. Although what I'm showing here is a PCI SPH. So it's a bit more advanced, also incompressible. And next, what we're going to look at is the other method using basically voxels. So the Eulerian method here, this is a simulation which is voxel based. So the domain of interest gets divided into 3D cells, and attributes are stored per time step in a voxel or in a cell. So let's just have a quick look at this. So do we have a, here we go. Cool. Let's grab my pen. Make sure we're on white. Basically, if we have a look at our liquid, so this is our simulation, and then instead of having just pure particles, if we just divide this up into a grid, for example. This is super basic and abstract, of course. And so if you would imagine this comparing to what I said before, where you're sitting in a boat traveling along. So for example, if you would sit in a boat, let's draw a boat here, like this. You're sitting in there. You would be traveling up here like that. And that's the Lagrangian method. And if we look at the Eulerian method, you would have the same. It's like as if you're sitting on a rock. So let's, I don't know, put that here. So this would be an invisible rock, basically this one voxel, and you're just looking at what is within your area, so your domain. So you're not going with it, you're staying at the same position and just basically storing the values here. So you're looking at how high is the water, stuff like that. I mean, this is obviously not how it would work in simulation, but just to give a visual idea how Eulerian compares to Lagrangian method. Yeah, so the attributes are stored per time step in each voxel, in each cell. And there are different algorithms to update these values, for example, via the advection. And it's easier to track mass since the problem is reduced to one single voxel instead of always have to calculate it between all the different points. Let me see, let's clear this. So basically, if we break this down to just a single voxel, we have, so this is our voxel, then we have our velocity in, and then basically you have some calculations, and then you have the velocity out. the incoming velocity defines the amount of mass entering. So basically how much mass from the neighboring voxel gets pushed into this cell. And after that, the amount of mass that leaves this cell is also defined by the V out. So basically how fast or how much it's going to move outwards. We'll come to this later. And the difference basically between the in and out, or between the out and the in velocity, is basically the divergence. So divergence is equals to, let's get these colors correct. So our velocity out minus our velocity in. And so basically, if our divergence is equals to 0, we have basically a divergence free, meaning a sim that is conserving mass and therefore not losing this over time. So basically, if you would fill up a container, for example, there would be no loss. Like if the amount of liquid that is entering, it would be kept inside the simulation, and not over time, like slowly getting less and less and less, which is a common issue. And so to sum this up, to provide a divergence-free sim, that's what we have to do to have mass conservation. And if we can do a new frame. So the only issue that we have with the Eulerian method is diffusion, meaning detail loss, for example, and also an energy loss. And I can explain this best if we just draw a one-dimensional grid. So if we have our grid here, and then we have another grid here, it should be the same. And then let's draw our fluid. So basically up here, everything is filled, a mass of 1. So 1, and then we advect, or we have a velocity. So V is equals to 1. Then what would happen in the next time step? The fluid from this cell would move to the next one. So basically would move here. Now this is an ideal situation, of course. This is something that would never happen. So assuming that the velocity is the same as the number of cells. So if I don't know, if we have a velocity of 2 or of 4, and that would basically represent the number of cells, and we would just only step from one cell into the next one, then we have no issue. So here this would be also a mass of 1. Now the problem comes in once we have just draw another grid here, different velocity. So basically a velocity of, for example, 0.5. So if we have here V is equals 0.5, then what would happen is basically our mass would move 0.5, so it would be sitting right in between those two. So basically half of this mass, which is 1, so 0.5, so 0.5. I'm just going to draw this with this, and then here as well. Let's just draw this like this. So that would be 0.5 and 0.5. And so this is obviously extreme, but so we're losing or diffusing basically our mass above those two voxels. And now in the next time step, basically, if we continue with the same amount of velocity, that would get even worse. So here in the first one, the blue, we would have 0.25, and since we also apply a velocity of 0.5. So basically half of this moves onto here. And then we have 0.25 here, 0.25 here. So basically we have, let me draw the last one. And then this one is the brighter one. Let me get my pen. So basically here, this gets divided by 2. So we are left with 0.25. Here we have basically this also divided by 2, because half of it moves out here, half of it moves there. So we have here 0.25 and then 0.25, and then this is 0.25. And so this is 0.5. So here this stays the same basically, because half of it from here drags into this one, and half of the one that, or basically half of this, which moves to the center of this point, stays in the original one. So 0.25 stays here, and 0.25 from this one, whichever the sum of it is 0.5. very, very confusing way of describing this, but I hope you get the point. And then this continues basically down the line. It just keeps diffusing more and more and more. Obviously this is, as I said before, extreme case, but just to showcase or show how diffusion, or why diffusion is happening, and why there is a detail loss. What the best would be, if you create a new background, is if we combine these methods to pick or flip. That's what they're called. So basically particle incel or fluid implicit particles. Basically they are more or less the same. There's just some small differences between pick and flip, which is in the look and also like the way it's transferring the velocity from the grid to the particles, which I'll explain in just a moment. And pick results in a more viscous look due to its velocity projection, but more on this in a second. So basically how this happens, if we would draw a simple grid, maybe if we can go in a bit. Let's just quickly draw a grid here, like this and this. And so here we would have a collider, and then we just have our points like this and this and this and this, and here another point here and here, and then our velocity would, for example, go like this and then like this. Just quickly draw some vectors. And first we have our initial grid, and what happens is basically the velocity gets stored onto the grid. So from the points, this is an average of the velocity. So we would, if we draw this grid again, so this is the first step. Second step, it's basically copying it onto our grid. Add in our collider. So we would then have our velocities, which would be the average would be something like this, and then this. I'm just noticing it's all straight, but doesn't matter. And then next, what is going to happen is it's going to calculate the forces. So if we, third step, draw another grid, and in this case that could be gravity, wind, collisions, as we're going to see in a moment here. So these are collisions, and then our corrected velocity, let's draw this in red. So this would still stay kind of the same. The corrected velocity for here is it's going to crash into here. Let's say it's going to go up. Here this is going to stay the same, and here it's going to have a slight upwards motion, and then this is going to stay the same. And then our next step is project that velocity back onto the points. So step 4. Like this, add in our collider. And let's draw back our points. So we had them here and here, here and here, here, there, and there. All right. And then, so basically our projected velocity gets transferred back onto those points would be for these points. It's basically staying the same. For this one, you get this upwards motion, and here as well. And then basically on the fourth step, which takes that velocity and then it vects the points. So, oops, that's got a bit crooked. Let's just draw it like that and then erase this out of there. Grab the pen again, collider. And now what happens is our points move forwards. So from, let's see, let's draw the original position here, 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 and here, here, and then the new position, which is basically with that velocity. Oops, wrong pen. Goes like that. And then this one we had here, and here we had these two, and then these went up, and this one to the side. So basically the new position of our particles would now be here at the end of that velocity. And this is step 5. And this is our basically the result of this, and this would just continue over and over and over again. Now, the difference between pick and flip here is that if you look at this, once this gets transferred back onto the points, for example, here you have multiple points in one cell, it's smoothing out the velocity. So for example, I mean, this was due to my bad drawing skills, but here, this point was going down, this one was going a bit more straight. And in the end, you just grabbing an average, because obviously you don't have enough cells to capture all the velocities that are, or all the points that are inside this one cell. And basically you have to take an average and then solving that and then transferring that back with the averaged velocity, so you get the same velocity for both of those, and therefore this results in a smoother look and feel and gives the pick method a more viscous kind of feel. And in flip, what happens is on step 2, where you're sampling the velocity of the points onto the grid, this grid gets stored. So let's see if we can get a color for flip here. Step 2, flip, copy. So basically it copies or duplicates this original grid, and then in the fourth step, where it's copying it back onto the points instead of just directly transferring it back onto the points, what it does, it subtracts the new grid. So this would be grid 4 minus grid 2, the new grid from basically the initial saved copy, and then it interpolates and adds the difference to the particle velocity, and therefore you get more detail because you're not going to have the exact same velocities for each point, so they can differ, but the general motion is going to be the same, and this helps counter the viscous feel. And so basically result of all this in the flip method is less averaging of motion. So I hope this wasn't too confusing. I could understand a bit what I was trying to explain here, how flip basically works. So it's like a hybrid between Eulerian and Lagrangian. The main sim is Lagrangian, but the solve of the motion, it all happens on a grid and just gets transferred back onto the points. and therefore is much faster, because all the stuff like the mass conservation, the forces, you're not calculating that on a per point basis. So like all the interaction forces that we have in a regular SPH solve, this is all eased up by using a Eulerian grid, or like a normal fluid pyrosim, if you would put it in a simple way. And so now in Houdini, since I'm not sure since which version they added this. So basically in Houdini, in addition to this, to the flip, the standard flip that we just discussed, is basically the narrowband. You've probably heard of this already. So what this does is basically it reduces the number of particles that need to be calculated, because it just seeds particles only on the surface, or where there would be a need for detailed simulations, and therefore saving a ton of simulation time and also particles, because the underlying pressure solve and stuff, that still happens, but you're not simulating all those particles. As you can see below here, you have the entire domain filled with particles, and in the top one you're just simulating the particles on the very surface where you actually need it, or where you actually need the detail. And the other thing that we have in Houdini 18 now is an adaptive pressure solve. So basically what this does is, I mean, it's not exactly what you see in the reference video here, but this is just to get a kind of an idea how this would work, or how this does work. The underlying pressure solve is basically, as you look at the image here, you can see everything that is very deep inside the surface, or deep inside the fluid, gets averaged and doesn't have to be very detailed in the calculation, and everything that gets closer to the surface needs more detail and simulation. And just by looking at this is, I mean, I love watching these kind of videos. It's just amazing. I was really waiting for a long time to have this implemented into Houdini. I mean, it's not the exact same, but the principles are kind of similar. On the detailed areas, you have high and more accurate simulations, and on the bottom, where you don't need that much detail, it's just all averaged out and basically saves some computation times. Not sure about the numbers, but yeah. So maybe just have a quick look at these videos here, and then I think we should be through the introduction to Flip. I hope this wasn't too confusing. Tried to break it down and make it as simple as possible. Obviously, due to making it simple, it's maybe not accurate in some points, but you can always go ahead and read upon this. There's tons of resource and a lot of great papers. It's really interesting reading through this stuff, what is currently getting developed. So next up would be the container setup in Houdini, where we get started with actually implementing what we just went through, and not really have to think about all this stuff, how this happens, but I think it's just good to know and have a basic understanding of how flip simulations work. And see you in the next section.